This is a six-wheeled rover which uses rocker buggy suspension mechanism for movement. The key principle of rocker buggy mechanism lies in its ability to adjust the position of the wheels to adapt to the terrain. When the rover encounters an obstacle, such as a large rock or a steep incline, the suspension system comes into action. The rocker arms on the side of the rover rises, while the other side lowers, creating a tilting motion. This tilting action helps to maintain stability and ensures the multiple wheels are always in contact with the ground in even or uneven surfaces. This is a differential mechanism. The differential mechanism is designed to distribute power and rotational forces between the wheels connected to it. It allows the wheels on the same side of the rover to rotate at different speed while maintaining power transmissions. The chassis is made of aluminum extrusions. Aluminum is a lightweight material. The characteristic is particularly beneficial for rover as it allows for reduced overall weight, enabling easier transportation and reducing the energy required for propulsion. Despite its lightweight nature, aluminum is known for its high strength, which ensures that the rover chassis can withstand the stress and vibrations experienced during operations. This strength is essential for maintaining the structural integrity of the rover and protecting its integral components.
So now we will be presenting our software stack which we plan on implementing in the actual bot. So first we will be launching the simulated environment in which the bot is going to run. So here, as you can see, a rough terrain has been generated with the bot spawned in it. So now we will be adding two obstacles in front of it which the bot has to avoid while trying to reach its goal. So now we proceed to the next step, that is visualizing the bot using RVs. In RVs, we can see the bot and the path it is trying to take by avoiding the obstacles. So here on the left side, RVs has been launched. Now we'll be sending some waypoints to the bot through a Python script which the bot has to move to while avoiding the obstacles. So now as you can see, the bot is trying to reach its destination while detecting its obstacle around it and simultaneously generating a path which can avoid all the obstacles in its path. Okay, so now we will be implementing obstacle detection using a LiDAR sensor. So basically a LiDAR sensor uses ultrasonic waves to measure the distance between the bot and the obstacle, and through MoveBase we can use that data and we can generate a cost map through which we can use path planning algorithm to generate the path of the bot around the obstacle. So first we'll be launching the required software, that is ROS, RVs and MoveBase. They are all integrated into a single launch file. Okay, so as you can see here, the RVs has been launched and we can see the cost map generated. Okay, so as you can see, this is the cost map generated, and there are the different regions in this cost map. Outer blue region depicts a low cost region. The inner light blue region depicts a high cost region, and the inner line is the lethal cost region. So these are the different layers of the cost map, and we can use these to generate a path planning algorithm. So we'll see how the obstacle layer moves when we tally up the bot. So as you can see, when I move the bot front and back and then turn it, the obstacle layer also changes. So this shows that the obstacle detection is working perfectly fine. Okay, so now we'll be calibrating the magnetometer values, which gives us the yaw data. So first let's understand what this is all about. We use magnetometer to give us a yaw value, which basically defines the angles rotated by the bot during a turn. Now, a magnetometer basically gives us the input as the x, y, and z component of magnetic field, and influenced by the Earth's magnetic field at that point. But there are certain disturbances caused by the soft iron and hard iron influence. Now, in order to cancel out these influence, we need to calibrate the magnetometer values. Okay, so the three values which you see on the left side of the black window are the three components of the magnetic field value. That is the X, Y, and Z component. Now we will be launching a package which will help us to calibrate these data. Okay, so the window which is appeared on the left side of the black window is basically a package which will help us to plot these data points and cancel out the disturbances. Okay, so first we'll be changing the true field strength of the point where I am in, and that is 46125.1 nanotesla. Now we'll be starting the calibration. So as you can see, the red dot is the current X, Y, and Z component of the magnetic field, and the blue points are the points which are already been passed by the bot. So when I rotate the bot, the points are plotted in a circular manner, but as you can see, the points are not completely circular in nature. Some points have gone up or down the line. So those are basically caused due to the disturbances. These disturbances can be caused by many items like the battery or the LiDAR or the GPS or any other Hall effect sensor. So this will allow us to cancel out the static magnetic disturbances. Okay, so now when I calibrate, you will see that a perfectly fine circular disk will be generated, and we get the calibrated values, which will be of a form of 4 cross 4 matrix, in which the top left 3 cross 3 matrix generates the rotation transformation, and the top left 1 cross 3 matrix basically defines the translation values, and the lower 3 cross 1 values will give us a scaling factor, which is generally 1.